Welcome to AI Paper Podcasts. It feels like every day there's another story about AI agents really taking off. And it's not just buzz. I mean, the market is valued at over, $5.2 billion this year? Yeah, and they're projecting it'll hit nearly $200 billion by 2034. It's just wild growth. But here's the interesting part. While everyone's focused on large language models, the LLMs powering these things, there's this fascinating new paper out from NVIDIA Research and Georgia Tech making a pretty bold claim, almost counterintuitive, really. They're arguing that small language models, SLMs, are actually the future for agentic AI.
Right.
Well, they say SLMs are already powerful enough. They're just inherently more suitable for how agents actually work operationally. And the big one, they're significantly cheaper.
Cheaper.
Yeah. The paper even talks about building these heterogeneous systems. So SLMs do most of the work, and you only bring in the big LLMs for the really tough stuff.
Kind of like specialist versus a general practitioner for everything.
Exactly. So today on AI Paper Podcast, we're diving into this paper. Small language models are the future of agentic AI. Our mission is to pull out the key insights for you, help you understand why this shift from LLMs to SLMs might be more than just a tech trend, maybe even a necessary step for the whole industry. Let's get into it. So the paper starts strong. It basically says the current way we rely on LLMs for AI agents is, and I quote, excessive and misaligned. That's fighting talk, isn't it?
It really is. And it's interesting because it goes against that bigger is always better mantra we hear so much in AI. Their core point is that most tasks agents do aren't, deep philosophical conversations. They're often repetitive, very specific, like extract this data or call that API, often not even conversational.
Okay.
And for those kinds of tasks, efficiency and predictability are king. That's where SLMs really come into their own. The authors kind of break it down into three main points, these value statements. V1 is principally sufficiently powerful. Basically, SLMs can do the job.
Right.
V2 is inherently more operationally suitable. They just fit better into the workflow.
Makes sense.
And V3, necessarily more economical. Pretty straightforward. They cost less to run and deploy.
Okay, so if we're maybe using a sledgehammer for a job that needs a scalpel, let's dig into that first point, V1. SLMs are already powerful enough. The paper says their capabilities have jumped significantly, and that the scaling curve, how much better they get as they get bigger, is getting steeper. What are you seeing there?
Oh, it's quite dramatic, actually. We're seeing this pattern everywhere. Models that are way smaller are matching, or sometimes even beating, much larger LLMs on tasks agents actually do. Take Microsoft's Phi series. Phi 2, that's only 2.7 billion parameters, right?
Tending compared to the big guys.
Exactly. And it's hitting common sense reasoning and code generation levels you'd expect from a 30 billion parameter model. And it runs something like 15 times faster. Then there's Phi 3, small, 7 billion parameters holding its own against 70 billion models. And it's not just Microsoft. NVIDIA's Nematron H family models from 2 to 9 billion params, they match 30 billion LLMs on following instructions and code gen accuracy. But, and this is key, with way fewer FLOPs, less computational work, Hugging Face has the small LM2 series, even down to 125 million parameters, performing like much bigger models from just a couple of years ago.
That's a real trend then.
Definitely.
Yeah.
There's NVIDIA's Himbo 1.5B, DeepSeek's R1 Distill series beating models like Claude 3.5 Sonnet and GPT-4o on common sense tasks. And maybe most relevant for agents, Salesforce's XLM-28B model is apparently state-of-the-art for tool calling, beating GPT-4o and Claude 3.5.
That's incredible. It really hammers home that size is the only thing that matters anymore.
Exactly right. And what's also fascinating is that you can boost their reasoning at inference time. You don't necessarily need a bigger base model. They mention techniques like using remember Toolformer? A 6.7 billion model outdid the 175 billion GPT-3 just by using APIs smartly.
Oh, right.
And we see similar things with math problems. Small models, like 1 to 3 billion parameters, can rival giants like 30 billion plus models if you give them structured reasoning methods at runtime. So the takeaway is clear. For agent tasks, it's about having the right capability, not just the highest parameter count. That's the real constraint.
That's a strong technical case, but maybe the killer argument, especially if you're running a business, is the economics. V3, right? The cost.
Absolutely. This is where it gets really compelling from a practical standpoint. The inference efficiency is just staggering. Running a 7 billion parameter SLM can be 10 to 30 times cheaper than a big 70 or 175 billion LLM.
10 to 30 times.
Yeah. In terms of latency, so fast responses, energy use, and the raw computation, the FLOPs, this makes real-time agent responses actually feasible at scale. And you have things like NVIDIA Dynamo now, which is basically an operating system for inference, designed to handle high throughput and low latency for these models, supporting SLMs in the cloud or even on edge devices.
And it's not just about running them day to day, is it? It's also about changing them, adapting them. That speed must be a huge advantage.
Huge. That's the fine-tuning agility. We have these parameter-efficient fine-tuning methods, now PEFT, like LoRa or Dora. These let you adapt a pre-trained model using much less data and compute power. You can tweak an SLM's behavior with just a few GPU hours of work.
A few hours. Seriously.
Yeah. Think about it. You could literally adjust how an agent performs overnight. Compare that to the weeks or months it might take to retrain or heavily fine-tune a massive LLM. That iteration speed is crucial.
And being able to deploy them not just in the cloud, but closer to where they're needed. That sounds like a big shift.
It really is. Edge deployment. You see things like ChatRTX showing SLMs running locally on regular consumer GPUs. That means real-time inference, offline capability, which is great for privacy and data control. No need to send potentially sensitive data to a cloud provider. And there's a more subtle point, too. Parameter utilization. LLMs are often sparse. Only a fraction of their billions of parameters are actually active for any given task. SLMs might be fundamentally more efficient because, well, they have fewer parameters to begin with, so more of them are likely contributing directly to the output, impacting the cost without necessarily hurting the quality for specific tasks. So if you zoom out, all this efficiency and agility leads to what the paper calls a Lego-like system design.
Lego-like.
Yeah, instead of one giant monolithic block, you build systems by snapping together smaller, specialized expert SLMs. This makes your whole agent system cheaper to build and run, much faster to debug if something goes wrong, easier to deploy updates to, and better aligned with the sheer variety of tasks agents need to do. Plus, there's a sustainability angle too. Less compute means a smaller carbon footprint.
That flexibility point really resonates. Lower training and tuning costs make it practical to have, say, a whole stable of specialized SLMs, each one an expert at a specific routine. You could spin up new ones quickly for new features or update them easily if regulations change, right?
Exactly. And this ties into a really important aspect, the democratization of agent development. If it's cheaper and easier to build and deploy these models, then more people, more organizations, smaller teams, they can all participate.
Right, not just the tech giants.
Precisely. You get a wider range of perspectives building these agents, which could lead to less systemic bias overall. It fosters more competition, more innovation, and just accelerates progress across the board. It's about opening up the field.
So thinking about how agents actually use language models, it seems like they often take a powerful LLM and heavily constrain it, right?
Yeah.
They feed it detailed instructions to perform a narrow task.
That's a key insight. Agentic interactions demand really tight behavioral alignment. When an agent needs to call a tool or produce output that code needs to parse, it absolutely has to stick to a specific format like JSON or XML.
Otherwise, things break.
Exactly. A general-purpose LLM, even with instructions, might occasionally hallucinate a slightly different format. That's a failure mode you want to avoid.
Yeah.
An SLM that's been fine-tuned specifically for that one required format is actually much more reliable and predictable in that constrained context. It's preferable.
And the paper mentions that these agent systems are naturally heterogeneous. One LM can call another, the agent's code can pick and choose.
Yeah, that modularity is powerful. Look at their figure 1. You could have a main LLM acting as an orchestrator, calling out to specialized SLMs for subtasks. Or you could have controller code managing everything, and all the language models involved could be specialized SLMs. Maybe one handles the chatty parts, others handle specific function calls.
Like a team of specialists coordinated by a manager.
Kind of, yeah. It gives you immense flexibility in architecture design for efficiency. And here's another neat aspect. These agent interactions are gold mines for training data. Because the prompts are often very precise and the tasks are narrow, each interaction is a high-quality example of instruction following. You can log this data securely, like that logger in Figure 1, and use it to continuously fine-tune your specialized SLMs, making them even better and cheaper to run over time. It creates this natural improvement cycle.
Okay, but no big claim goes unchallenged. The paper addresses the skeptics too, right? What about the argument that LLMs, being generalists, just have a fundamental advantage? People point to scaling laws, bigger models perform better, or this idea of a semantic hub where LLMs integrate knowledge more deeply. How does the paper counter that?
It tackles it head on. First, scaling laws often assume you're just making the same architecture bigger. But SLMs aren't always just shrunken SLMs. They can have different optimized architectures that perform better at smaller scales.
Yeah, so it's not an apples-to-apples comparison.
Not always. Second, the flexibility factor again. You can easily fine-tune an SLM for a specific task to get the reliability you need. Scaling law studies usually look at general zero-shot performance, not this kind of specialization. And third, scaling compute at test time, making the model think harder during inference, is way cheaper and more feasible for an SLM than a massive LLM. As for the semantic hub, the paper argues its real benefit is for truly complex, nuanced inputs. But good agent design often involves breaking down complex problems into simpler subtasks before handing them to an LM.
So the SLM gets a manageable piece.
Exactly. In that context, the supposed advantage of a deep, abstract semantic hub becomes less relevant for the actual task the SLM is performing.
Okay, what about the other big counter-argument? Economies of scale. The idea that running one huge centralized LM service is ultimately cheaper because you can balance the load better, even if individual SLM inferences are cheaper. Plus, setting up all that SLM infrastructure isn't free.
That's a fair point, and the paper acknowledges it can be true depending on the specific situation. It's case-specific. But it also points out that things are changing fast. New developments in inference scheduling and system modularization, again, think NVIDIA Dynamo, are making it much easier to efficiently manage lots of SLM endpoints within large clusters. The old load balancing challenges are being addressed.
And the setup costs.
Those are consistently dropping. The underlying tech for running inference is just getting cheaper and more accessible all the time. So, while it's a valid concern now, the trend lines favor SLMs.
And the last one, simple inertia. The LLM world has a head start, tons of investment, existing tools. Maybe the industry just locked in that path.
Yeah, the paper calls this industry inertia. It's definitely a possibility. Habits form, investments are made. But the authors maintain that the combined weight of all the SLM advantages, the power, the suitability, the economics, the flexibility, is strong enough that it can plausibly shift the momentum. It's arguing for a necessary evolution driven by fundamental benefits, not just hoping for a change.
So, if the case for SLMs is so strong, why aren't we seeing them everywhere in agents already? You touched on it, but what are the main blockers?
Right, it's a critical question. The paper points to three main practical hurdles, not fundamental flaws, mind you. First is upfront investment. Billions have already been poured into centralized LLM infrastructure. Tooling, expertise. It's all geared towards that right now. Switching requires effort and potentially new investment, creating inertia.
Path of least resistance.
Pretty much. Second, generalist benchmarks. A lot of SLM development, maybe paradoxically, has tried to make them good at the same general tasks LLMs excel at using the same broad benchmarks. But if you evaluate them on benchmarks specifically designed for agentic utility, how well they perform specific agent tasks like tool use or following formatting rules, SLMs often blow larger models out of the water. We're potentially measuring the wrong thing.
Interesting. Misaligned incentives, almost.
Could be. And the third barrier is just lack of awareness. LLMs get all the headlines, all the hype. SLMs, despite being workhorses in many potential industrial scenarios, just don't get the same press or marketing push. But again, these are practical issues. Technology like better inference scheduling is tackling barrier 1, the field is waking up to barrier 2, and barrier 3 might just solve itself as the economic benefits become undeniable.
And the paper doesn't just diagnose the issue, it offers the solution, right? This LLM-to-SLM agent conversion algorithm. It sounds like a roadmap.
It really is. It lays out a practical step-by-step process for migrating agent applications. Step 1, S1, secure usage data collection. You need to log what your agent is actually doing, the inputs it gets, the outputs it produces, the tools it calls, how long it takes, and crucially, do this securely and anonymized, protecting user data.
Gotta have the data.
Absolutely. Then, S2, data curation and filtering. Get enough examples, maybe 10K to 100K, and then meticulously clean it. Remove any personal info, sensitive data, maybe using automated masking or paraphrasing tools. You need clean, safe data for training.
Okay, clean data acquired. What's next?
S3, task clustering. You use unsupervised machine learning, basically, to sift through that data and find patterns. What kinds of tasks is the agent really doing repeatedly? This helps you define specific roles for your specialized SLMs, maybe one for recognizing user intent, one for extracting certain data types, one for generating code to call a specific API.
Identifying the jobs for the specialists.
Exactly. Then S4, SLM Selection. Based on those defined tasks, you pick candidate SLMs, you look at their capabilities, how they do on relevant benchmarks, their license, how easy they are to deploy, maybe picking from models like Phi or Nemotron H that we talked about earlier.
Makes sense. Choose the right tool for the job.
Right. And then S5, specialized SLM fine-tuning. You take your curated data for a specific task cluster and fine-tune your chosen SLM. You can use those efficient PFT techniques like LoRa or maybe knowledge distillation training the SLM to mimic a more powerful LLM just on that one task.
Transferring the knowledge without the overhead.
Precisely. And finally, S6, iteration and refinement. This isn't a one-off. You set up a loop. Keep collecting data, periodically retrain your SLMs and any models routing tasks to them, adapting as user behavior changes or new needs emerge.
A continuous improvement cycle. That sounds really practical.
Yeah.
And they showed it works in practice. Mentioned some case studies.
Yeah, briefly. They estimated potential replacement rates in existing agent systems. For MetaGPT, maybe 60% of LLM calls could be replaced by SLMs. For Open Operator, around 40%. For Cradle, potentially 70%.
Whoa, 70%.
Yeah, it shows there's real tangible potential to swap out expensive LLM calls for cheaper, faster SLM calls in a significant chunk of agent workflows.
Okay, so wrapping this up, the core message from this NVIDIA and Georgia Tech paper is pretty clear.
Right.
SLMs aren't just niche players. They argue they are powerful enough, better suited operationally, and way more economical for the bulk of agentic AI tasks.
Yeah.
It's positioned as the future.
Right, and they connect it to that broader idea, the Humean moral ought. The cost savings, the energy efficiency, the sustainability gains. These aren't just nice to have. They argue these factors are essential catalysts for making agentic AI truly transformative and widely adopted ethically and practically. It's about enabling the revolution responsibly.
So here's something for you to chew on. If this shift to SLM-first architectures really takes hold, what does that mean down the road? How could it change who gets to build AI agents, what kinds of agents we see, and how they impact our work and lives? Could it unlock innovation or applications we aren't even considering right now, simply by making sophisticated AI more accessible and efficient?